to our idea of chance is the word contingency. And contingencies are, of course, very common, very familiar to anybody who has run a research grant, because a multitude of sins are hidden under the consumables and contingency part of your grant. But a contingency is a future event or circumstance which is possible but cannot be predicted with certainty. What is characteristic about a contingent event is that it is not a necessary event. The absence of necessity, the fact of something having to be without having to be so. So this is an idea that we all live with, and in a variety of situations we are actually familiar with contingencies, as in not just in grants, but in contingent plans, contingent events, and so on. Famously, Friedrich Engels said that freedom was the recognition of necessity. I was recalling this because a similar statement was made by another Marxist thinker, D.D. Kosambi, whose first job, as it happens, was at the Banaras Hindu University in 1930. He was here for 2 years, between 30 and 32, teaching mathematics and German, as it happened. And he said that science was the cognition of necessity. It sort of abbreviated the Engels statement. And what I'd like to do is to add a little to that and say that chance is the absence of necessity. Things do not have to happen, but they do. The fact of being so without having to be so. Now, when we think of chance in a scientific context, we actually do a fair amount. This chance could be due either to incomplete or imprecise knowledge. That is, you don't know everything about the system, so it behaves in a way which you cannot predict. This is a very deterministic approach to how one thinks about science. So a chance event may be due to incomplete or imprecise knowledge, and such chance I will call, not I, but it is generally called epistemological. Okay, so the causes of this uncertainty is because of a lack of full knowledge. And there is another kind of chance that we are all very, very familiar with, particularly in a quantum mechanical context, where you have uncertainties. And I will not be speaking of quantum mechanics, though all my talk really is about classical ideas. So chance can also arise from intrinsic fluctuations in the system, and this is ontological chance. So it's either epistemological or ontological. So a basic something, which is not because you didn't know as much as possible. Now, in diverse situations, chance plays a major role. And I'm just quoting two thinkers and major scientists of the last century. Jacques Monod had a very famous book called Chance and Necessity, and I'll come back to that later on. But nature relies on chance and not on destiny, just to paraphrase what Monod thought. And C.R. Rao, the famous statistician, wrote a book in 1989 called Statistics and Truth. And there he says, chance may be the antithesis of all laws, but the way out is to discover the laws of chance. And this is something that people who work in dynamics and so on have been worrying about for about 50 years now. The idea that chance could be found useful goes back to an old experiment, or an old thought experiment of Buffon, who was a count in France at some point in time. And he asked the following question. I'm sure this is familiar to almost all of you, but let me just talk about a way in which chance brings out unexpected things. So the Buffon needle problem is the following. Given a floor which has got wooden, let's say, which is made out of planks of wood, and these are parallel strips, if you take a needle which is a little smaller than the width between these lines, so you think of the floor as having these slats of wood, and the wood has got, the width of each of these is T, and the length of the needle is L. If you just drop it, if you drop the needle by, it'll fall in some particular way, and you want to know what is the probability that it is going to cross one of these boundaries. Now, this is a sort of an archetypical idea of what we think of as a chance event. You toss a coin or you throw a needle. This is the way in which you think about it. Now, the needle can only cross the boundary if the center of the needle lies within a certain distance of the boundary, and if it cuts, if the angle which it will take randomly, which will also be appropriate. Now, there's a little mathematics, all of which can be found in Wikipedia, but it turns out that if theta is the angle that a needle makes with the vertical, this, the probability that it will cut the boundary is just this quantity. It can be worked out as a small integral to be done, but the probability is equal to 2 times the length of the needle divided by the width of the slats times pi. So what was very unusual and what is talked about in the context of Buffon's needle problem is the unexpected occurrence of pi over here. And it is a fact that if you take a needle, or if you take 1,000 needles and you drop them, and again you can do this very conveniently on the computer, you will actually find that if you drop it n times and it crosses the boundary c times, then you get a very nice approximation for pi. And this is entirely by a little game of chance. So, I mean, this, of course, is a very, a particular example, but it's not just amusing. It tells us how things happen randomly in real life. And some people have gone and computed pi this way. It usually figures in my introductory courses in computational physics, but this is the basis of all sorts of Monte Carlo methods, that how do you evaluate something probabilistically, even if you don't know how to do it analytically. In biology, of course, chance has played a very, very major role. To the best of our knowledge, the origin of life itself is very likely to have been a chance event. We know that there is life on Earth, but we are not sure whether there is life anywhere else. How singular is this event? Now, okay, so that is one place where chance plays a major role in biology. Another role, which is more easily documented in some ways, is the role of chance as the determinant in natural selection. We all know that genetic information is transmitted through the DNA, but we also know that this happens not by making perfect copies, but by making imperfect copies. And the imperfection over here, the wonderful book of the title In Praise of Imperfection, but the imperfection gives rise to diversity, and this diversity allows for natural selection. Any very singular event, that which happened only once, is something that happened without having to happen. Namely, again, it's an occurrence of chance, and we know that life on Earth is divided broadly into 2 categories, the eukaryotes and the prokaryotes. Prokaryotes were an earlier form of life, and the eukaryotic form developed from the prokaryote. And that also did not happen too often. In fact, people think that it probably happened just once. Again, it was an occurrence by chance, because for a billion years or so, all life on Earth was just of the prokaryotic type. And our being in this room, not in the sort of the trivial way of us coming together because of invitations and so on, but the fact that mammalian species are the dominant species on Earth today arguably happened because a meteorite crashed into the Yucatan or some place. There are competing theories, I know. But there was a random celestial phenomenon of a meteorite coming close enough to Earth to actually cause the extinction of the dinosaurs. So that was also not something that keeps happening, although we do have meteorites, but not such large ones and not so often. Chance has played a major role in biology in a variety of different ways. And this is in contrast to how by we, I mean, let's say largely, quantitative scientists, physicists, have described the physical world for a long time. What I have over here is a model of Kepler's model of the solar system, where Kepler thought, or the imagination was, that there are some perfect Platonic solids. These perfect Platonic solids describe the way in which the orbits of the major planets are organized around the sun. So we like, as a race of scientists, if you like, as a race of thinkers, we like simple laws, we like elegant laws, we like beautiful or symmetric laws. But what is the actual nature of the world around us? Because the real world is somewhat more messy than what these lovely little pictures will show. And where, if at all, do events which are random, which are like chance-like, where do they come up in this scenario, or in this way of thinking about the world? Einstein put it succinctly. He pointed out that our descriptions of nature are very approximate. He says, as far as the laws of mathematics refer to reality, they're not certain. And as far as they are certain, they do not refer to reality. Now, of course, he was also, he was being combative with quantum mechanics and so on, but still, this is a genuine concern that you may have, that if you have extremely simple, elegant, beautiful, symmetric laws, do they really talk about the world around us, or are they just approximations of the world? Now, what has changed since the time when Keplerian and Newtonian physics, etc., started dominating the way in which quantitative scientists make theories, is the recognition that nonlinear science is an extremely important way in which you have to modify some of these simple ideas, or simpler ideas have to give rise to include nonlinearity. Now, the appropriate mathematics that we need is often nonlinear. And nonlinear systems often have solutions that cannot very easily be described. The hardest problem in the world, at least according to Clay, the Clay Mathematical Institute gives $1 million to anybody who can solve the Navier-Stokes equation, or talk about some special solutions of the Navier-Stokes equation, nonlinear systems. Now, predicting what happens in a nonlinear system over a long period of time turns out to be a very difficult matter, and these solutions are fundamentally complex. Now, this has had a profound implication both for the way in which we understand nature and actually for how it impacts technology, whether it be to making better machines, or machines that would do jobs in the way that you want. Uh, Mechanical objects or machines or technology is the antithesis of unpredictable systems, because you don't want such a system to not be reliable. So all of technology really relies on reliability, and nonlinearity has a very nasty way of coming up against that. Now, as all of you know, certainly, um, chaos theory, which came up in the 60s and has been an important component of many, many disciplines since then, chaos theory has actually changed the way in which we think about nonlinear systems, and we've come to realize that there is a way of understanding irregular behavior, both in space and in time, and to look at its consequences. In a way, this is a partial answer to C.R. Rao's challenge, if it were, that the way out is to try to discover the laws of chance, and I'll try to explain why. Now, a system doesn't have to be very complicated to be unpredictable. The archetypical example of an unpredictable system, and one which we use every day or every time there is a cricket match or any kind of match, is to decide on one of two possibilities by tossing a coin. We believe that the outcome is random. How random is a coin toss is another matter, but still, we know today that there are many systems, very simple ones, that behave in a manner which is akin to the tossing of a coin. One of the icons of chaos theory and nonlinear science has been the Lorenz system, or what's known as the Lorenz butterfly. This is a system that came out of the study of meteorology, and it actually is a truncation of the Navier-Stokes equation, but all that is really not very important. The Lorenz system heralded the birth of the study of chaos and irregular behavior in the following, through the following set of paradigms. The equations themselves are very, very simple. They are almost linear, and linear systems, as I already indicated, are things that we understand very well. But the simple nonlinearities that are over here are this particular term and this particular term. So there are very few nonlinearities in this system. And yet, for a set of parameters, it's not always important what these parameters are, the solutions of this system are really fundamentally complex. And they are complex in the following way. If you start out at any point, in time, the orbit will trace out this rather beautiful looking object, but in a very unpredictable fashion. Namely, it could come winding down. It could come winding down here several times and there several times, and flop back and forth between these two branches or these two wings in a completely unpredictable manner. I shouldn't say completely unpredictable manner, because these equations, nothing, or arguably they are very simple. And of course, it can be predicted from this. But they are unpredictable in the following way. Were I to start at this initial condition and go follow the trajectory for a little while, I would, let us say, land up over here. But were I to start ever so close to that initial condition with a red-colored pen and go for the same amount of time, pretty soon what happens is that the red and the blue diverge from one another, and the red trajectory, so to speak, ends up over there, whereas the blue came here. So this is what is called sensitivity to initial conditions, and more commonly, this is chaos. So you have an object with very simple equations whose long-term behavior you cannot actually predict because it has very sensitive dependence on initial condition. At the same time, if I were to start over here, I come back onto the object. If I start over here, I also come back onto the object. So no matter where I start, I come back onto an object which is the same, but on the object, I don't know where I am. So I'm unpredictable in the small and completely predictable in the large. So no matter where I start, I go on to that. But when I start on the object, I don't know where I'm going to be. Now, this gave, in common parlance, another very important idea, the idea of attractors. So one thinks that the Lorenz system and many other systems have attractors, and these attractors attract every initial condition. So the inevitability of going to this particular final state is guaranteed by the structure of the equations themselves. There is this object which exists, and wherever you start, you will eventually go there. Now, where does chance come about in all this, you say? It turns out that actually you don't have to have a single attractor, you can have many of them. And even in this image, there's one attractor which is obvious, which is where these trajectories are circling. But at the very center of these two wings of the butterfly, so to speak, there are two other attractors, very simple ones. And the way in which it happens in such systems is that you start at one particular point, and the start is indicated by one of these squares. You may land up at a particular attractor. You start somewhere else, you may also land up at that attractor. You start somewhere else, you are at another attractor or another or another. You can have many different attractors. This is actually common in many, many systems, and I will argue that the fact of having many attractors is exploited by nature. What is interesting about these attractors is that all the points that go to a particular attractor is called the basin of the attractor, and the basins of these attractors turn out to have very interesting geometries. In the Lorenz system, if I start with initial conditions over here in these green and yellow regions, I go to the fixed point. If I start in the blue region, I go to the chaotic attractor. So where I am, my present determines my future, both quantitatively and qualitatively. This idea is called multistability, and multistability is the basis of all switches. The fact that you can have more than one stable asymptotic state allows you to have a switch or to make a switch. And as we know in many, many examples in different fields, the switches are crucial, not just in engineering and such applications, but you want to have switches in sensors, you want to have switches in biological systems, and so on. And the fundamental thing that lies at the heart of a switch is to have a system with more than one stable state, that is either bistability if you have two, or multistability if you have many. Now, the existence of many attractors actually makes systems very complicated. And I will briefly touch upon them. Well, if there are several attractors in a system, it turns out that the basins that each of these attractors possesses can be complex in one of two ways. They can either have complicated boundaries. I will skip over this and just point out the complexity. They can have complicated boundaries. As you can see over here, There are three attractors at the center of these three dots. All the points that go to the yellow attractor are marked in this yellow color, all to the green are marked in green, and all these in blue. And there are sort of very interesting structure is what the basin forms. And the basins can be even more complicatedly intertwined with one another. And this is where chance begins to play a role. The idea is one of riddling. If the basin of one attractor is arbitrarily close to basins of the other attractor, then we say that one basin is riddled with respect to the other. When two of them are riddled with respect to each other, then it turns out that the image looks like this. All the black points go to one attractor, all the white points go to another, but arbitrarily close to every black point is a white point. And so you see that if I just draw the basins, they look like so, and if I were to enlarge this little portion out here, it looks pretty much like itself all over again. So there is no hope that improving numerical accuracy can ever rid you of this kind of uncertainty. Now, this kind of property is actually alarmingly common in most systems. In fact, this underlies the kind of uncertainty and gives importance to the role of chance in most physical systems. Because, as I just said, the boundaries themselves can be smooth or they can be fractal, they can be very, very complicated. They can be riddled or intermingled. And then there is an interesting mathematical property that they have, which is known as the Wada property, after a Japanese mathematician, Wada, that every point on the boundary of a basin is close to, or it's in the neighborhood of two or more other basins. So no matter where you are, you're always very, very close to the possibility of having done something else. Now, this is really what chance is all about, that you cannot, with any sense of certainty, predict where you're going to go, because in a sense, your hands are tied. There are several possibilities, and each possibility comes arbitrarily close to every other possibility. And in the literature, it's called final state sensitivity. And this provides a very natural setting for how chance arises in purely deterministic systems. The only thing that we don't know precisely, and it is the cause of the epistemological origin of chance over here, we don't know our initial conditions perfectly. But what is perfection when the other possibility is arbitrarily close to you all the time? So even when the equations are known, parameters are known, the nature of these attractors and their basins can make a prediction of the final states very, very difficult. And this allows systems to experiment with very interesting states, which are mixtures of periodic and completely incoherent dynamics. And I have talked about this earlier in Bhopal, for those of you who were there, as the chimeric state, where you have both deterministic or both purely predictable and incoherent dynamics coexisting. This happens largely because you have attractor basins that are intermingled and completely meshed in with each other. No matter where you start, you could always have done something else. There is another kind of chance that happens, and this is very familiar in biological systems. This kind of chance is also frequently known as arising from intrinsic noise, and it is a consequence of the size and the scope of biological systems. Now, as all of you know and better than I, cells are small and very crowded. They are packed with stuff. They are largely water, but there are small molecules, there's DNA, there's RNA, there's proteins, lipids, which are slightly larger. So the entire cell is actually a very, very packed environment. And it's almost a wonder that things happen as they do. Because as we also realize in biology, timing and organization are of the essence. And when they are of the essence, we need to be able to assert that certain things happen definitively. And in such a packed environment, where the ribosomes are, which are shown in green, the RNA molecules are shown in blue, and the proteins are in red, stuff is happening all the time, stuff is being produced, and very complex sets of organizations are happening. How does this occur? So noisy, and this is the sort of typical cellular environment. It's noisy, and it is noisy in a way in which we cannot tune out. In many physical systems, you can lower the temperature and lower it to a state of zero entropy. And that kind of tuning out of uncertainty or disorder is something that one can do in a physical system because your source of disorder is coming from the outside. Here, on the other hand, the disorder comes from within the environment, and I'll just explain that if you've got such a packed environment, how does a reaction take place? And this environment is filled with physical obstacles. There are passageways and very complex organization happening. So chance actually plays a major role in a biological environment because in order for a reaction, a chemical reaction to happen, the two entities or more than two entities that are participating have got to find each other first. And when you've got a very packed environment, which is just occupied by all sorts of stuff, that's a matter of chance. So individual chemical reactions are actually random events, and they at the absolutely microscopic scale. And when the numbers are small, these random events happen even more rarely. A purely random event is usually described mathematically by a Poisson process. When you've got many reactions which are all random events happening, you've got competing Poisson processes, and this is another source of stochasticity in this environment. It's not just a cell where this is important. It so happens that the nanoscale is something that we are all very familiar with these days. So many reactions, when they take place at the nanoscale or in a nanoscalar environment, either in a laboratory or in a catalyst or in interstellar space on dust, these kinds of reactions all happen stochastically. Especially you can imagine a lonely molecule sitting on a dust particle as it hurtles through the universe, waiting to find another molecule to react with. It could take a long, long time. Okay, so this way of studying chemical kinetics is stochastic reaction kinetics, and this is now a part of the way in which many biological models are studied. These, the basic thing over here is that we go away from the chemist's notion of concentrations and go over into looking at events in terms of numbers of molecules. And each of these reactions don't happen by, the intrinsic quantity that goes into forming a reaction rate is the rate of a Poisson process. And the way in which a stochasticity shows up is that both the time of each reaction and which of the possible competing reactions it would be, these turn out to be probabilistic events, and they are intrinsically probabilistic rather than because you don't know some initial conditions and so on. Right. Very briefly, just to show you an example of the difference between these two approaches, there's a well-known model due to Goodwin of a biochemical oscillator, which, I mean, this is the sketch of this biochemical oscillator, and details are not important. But were one to study it as a macroscopic chemist, you study the following differential equations. Were one to study it as a stochastic modeler, one would come up with these kinds of processes for 6 possible reactions. And the differences are actually substantial. Deterministically, this is the behavior, damped oscillations. Stochastically, each time this reaction happens, the fluctuations are huge. So the contrast between pure knowledge and pure chance is really it lies in the fluctuations. And here's for another set of parameters for those who are interested. Now, all chemical and biochemical reactions at the cellular and subcellular levels are therefore subject to very large fluctuations merely because chance plays a role over here. Right? Now, this is for almost a trivial model of a biochemical system, but most biological networks, those that describe anything of interest to us, are complex. They allow for distinct dynamical states to exist, which is why you can use them as switches and so on. And therefore, in such cases, there's the possibility that small changes in the initial environment can lead to very large changes in the outcomes. This gives rise to complex patterns in space and time, and by exploiting such complexity, a system can explore new behavior in responding to the environment. Now, this is extremely important because of our history as a species. From Darwin onwards, it has been one of the sort of guiding lessons of biology that life itself is a game of chance, and the causation, what made things happen, is a matter of context. Now, chance signifies possibility, and thus it gives you a freedom to create. I'm thinking more in terms of how a chance mutation may endow an organism with a particular ability to survive in an environment. And this, of course, we have examples of this all over the place, famously in sickle cell anemia, where one mutation gave rise to the possibility of survival over and above other. Jacques Monod, in a famous and somewhat controversial essay on chance and necessity, he says that life appeared on Earth, but what happened before the event? What were the chances that this would happen? The present structure of the biosphere far from excludes the possibility that the decisive event happened only once. It could have happened and not succeeded, and happened and not succeeded, and so on. This means that the a priori possibility of life coming about, that probability was virtually zero. And yet we are here, of course. Our universe was not pregnant with life, nor the biosphere with man. Our number just came up in the Monte Carlo game. I find that profound. Now, whether or not it derives from processes that follow deterministic laws, chance is a fundamental and unavoidable reality. This ought to be viewed as a good thing. For if it were not so, then we would not be here to ponder the seeming improbability of our own existence. Thank you.